Physics is the foundational science that explains how our world functions. It governs motion, energy, light, and matter, not only in laboratories and classrooms, but in every moment of our daily lives. Often we overlook the physical principles shaping the environment around us, yet with closer observations, we find physics embedded in the simplest and most familiar scenes. Today, we will examine how everyday experience, from falling leaves to the glow of a light bulb, are united by the same laws of nature, revealing the deep connection that physics creates throughout our world. Let's begin with something simple and recognizable. A falling leaf in autumn. When a leaf detaches from its branch, it rarely falls straight down. Instead, it twists, spirals, and glides through the air. This motion results from a delicate interaction between gravity and air resistance. Gravity pulls the leaf toward the ground, while the broad, flexible surface of the leaf interacts with the air, creating tiny whirlpools of turbulence. These swirling currents push the leaf from side to side, giving it that graceful fluttering descent. What appears to be a peaceful moment in nature is actually a dynamic demonstration of aerodynamic forces at work. Now let's shift our focus to another object, shaped by wind. A flag. When a flag flutters, its movement is not random. It responds to a physical process known as vortex shedding. As air flows past the edge of the fabric, it forms alternating, swirling pockets of air that push the flag back and forth in wave-like pattern. The same fluid dynamics that govern the twisting path of a leaf also dictate the rippling motion of a flag. Even in a gentle breeze, physics is shaping every curve, snap, and wave. But there is even more happening beneath the surface. A flag is not perfectly stiff, it bends, stretches, and twists. This flexibility creates constantly changing shapes, and those shapes influence how the air moves around the fabric. The wind changes the flag, and the flag changes the wind in return. The continuous interaction is what makes the motion so lively and unpredictable. The fluttering we see is actually the result of a complicating balance between aerodynamic forces trying to push the fabric and elastic forces inside the material, trying to restore its shape. In other words, the flag is constantly negotiating with the wind. Different conditions can dramatically change the behavior. A strong gust may stretch the flag tight and cause it to snap sharply, while lighter winds allow smooth rolling waves to travel down the fabric. Even the shape and texture of the flag, whether it has frayed edges, seams, or wrinkles, can alter the airflow and create new patterns of motion. What appears to be simple fabric waving is actually a dynamic system reacting to ever-changing forces in the environment. Flags also provide a practical lessons in physics. Engineers study vortex shedding to design safer buildings, bridges, and antennas. If wind creates vortex that match the natural vibration of a structure, the result can be dangerous oscillations. The same physical principle that makes a flag flap can make tall structures sway or even fail. Understanding how air behaves around flexible materials helps scientists and engineers prevent damage and build designs that can withstand the elements. So while a flag on a breezy day can seem like a decorative symbol, it also a real-world demonstration of complex physical law. The shifting pattern of its motion is how air flows, how forces interact, and how material responds. Just like the drifting leaf, the waving flag reminds us that physics is always active, shaping the everyday scenes we often overlook. But physics extends far beyond motion. It also governs how energy is stored, transformed, and used. To see this, we travel deep underground to the physics of coal. Coal is, in a sense, ancient sunlight. Millions of years ago, plants captured energy from the sun through photosynthesis. As those plants decayed and were buried beneath layers of sediment, pressure and heat slowly converted them into coal. The energy that originated in sunlight remains locked inside the chemical bonds of carbon. When coal burns, those bonds break and release heat. That heat turns into water, into steam. Steam spins a turbine, and the turbine produces electricity. Cole demonstrates a fundamental principle: energy is never lost, it only changes forms. This brings us to a far more familiar source of light, a ceiling lamp. With a simple flip of a switch, electrical energy flows into the bulb. In traditional bulbs, that electricity heats a thin metal filament until it glows, producing both light and heat. In modern LED bulbs, electrons move through a semiconductor material, releasing photons, the building blocks of light. What feels like everyday convenience is really another transformation of energy. What was once stored in the earth can ultimately become the soft illumination in a living room. And finally, stained glass. Here I'll dive a little bit deeper. Stained glass represents one of the most elegant ways physics appears in art. Its vivid colors come from carefully selected metal ions and compounds added to molten glass. Cobalt ions create deep blues, copper produces greens and turquoise tones, and tiny particles of gold generate brilliant reds. Each metal changes the internal electron energy levels of the glass. When white light strikes the surface, photons with specific energies are observed by those electrons. While others wavelengths pass through, the colors we see are simply the wavelengths that remain, a direct result of quantum interactions happening at a microscopic scale. But the physics does not stop at color. Glass itself has a higher index of refraction than air, meaning light slows down as it enters the material. This shift in speed causes the light to bend or refract, which is why stained glass glows differently depending on the angle of illumination. Many panels are intentionally textured or etched, creating tiny surfaces that scatter and diffuse light. Instead of traveling straight through, light spreads in many directions, producing a soft radiant effect that transfers plain daylight into something visually dramatic. In places like cathedrals or historic buildings, another layer of physics emerges. The constantly changing position of the sun alters how light interacts with each pan. The moving sun acts like a dynamic spotlight, casting evolving patterns of color across walls and floors. Even the thickness of the glass or the bubbles trapped inside can alter how light refracts, adding depth and variation to the imagery. What looks like a still object is actually participating in a continuous optical performance. Stained glass reminds us that physics is not only responsible for motion and energy, it is also responsible for beauty. Behind every glowing panel is a combination of materials science, optics, and quantum physics, working together to turn ordinary light into something extraordinary. It is a perfect example how understanding the laws of nature can reveal an even deeper appreciation for the art we see. So, from the motion of leaves to the movements of flags, from energy stored in coal to the light that illuminates our homes, and finally to the vivid beauty of stained glass, we uncover a powerful truth. Every moment in our world is shaped by the same universal laws of physics. What first appears to be separate, nature, technology, and art, is in reality deeply interconnected. Each example is a different expression of the same principles that govern how energy flows, how matter responds, and how light behaves. Physics is not an isolated subject reserved for scientists. It is the framework that explains how the universe operates. Whenever something moves, glows, bends, burns, or changes form, physics is the invisible force guiding it. It transforms what we experience into something understandable. What might feel like everyday routine, a lift drifting downward or light switching on, is actually part of a much larger scientific narrative unfolding around us. Each moments that appear purely artistic or emotional, like watching sunlight filter through stained glass, are supported by precise physical interactions. We're not just seeing color, we are witnessing the behavior of photons, the structure of atoms, and the pathways of materials shaped by human creativity. The beauty that reaches our eyes has traveled through a journey of refraction, absorption, and transformation, all governed by physical laws. Recognizing these connections changes the way we look at the world. Suddenly, a falling leaf is not just part of autumn, it is a demonstration of gravity and turbulence. A flag in the wind becomes a lesson in fluid dynamics. A glowing light bulb is a reminder of energy changing form. Stained glass becomes a window into quantum physics and optical science. Physics turns the ordinary into something extraordinary. So the next time you feel a breeze, watch a leaf descend, turn on a light, or admire the shifting colors cast across a floor by stained glass, pause for a moment. Understand that you're witnessing physics in action, the same physics that shapes planets and stars, guiding the smallest details of our surroundings. The universe is always telling its story quietly and consistently through every motion, every transformation, and every beam of light we see. Thank you for watching.